Assalamualaikum warahmatullahi taala wabarakatuh. I'm Dr. Sababau from the Physics Sections, Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This course JRF 4318, Quantum Mechanics. We are in Chapter 1, Introduction to Quantum Physics. In this segment, which is Unit 1.3, we'll discuss blackbody radiation again, but concerning Planck's hypothesis. The objective of this segment is that you will be able to describe how Planck managed to describe the spectrum of blackbody radiation. If you remember Boltzmann's distribution, Boltzmann considered a collection of interacting particles such as radiation in a blackbody cavity from thermodynamics. This is classical physics, okay? The average energy of this particle E bar is equal to kT. That means the average energy is directly proportional to temperature. If we pick a random particle in the energy distribution, we can define PE dE to be the probability that the particle has energy between E and E plus dE. Okay, so P is the probability of finding a particle between E, energy E, and energy E plus delta E. That means the difference or the region in the range of delta dE. Yeah? P is called the Boltzmann distribution. It's defined here. P equal to E exponential negative E per kT divided by kT. This is the Boltzmann distribution. The mean energy of the particle equal to, we integrate P E dE divide by integrate 0 to infinity P dE equal to kT. Okay, that's how we get the mean energy if we use Boltzmann method. Okay, if we use Boltzmann distribution, we still end up with Rayleigh-Jeans formula because as I said in the previous segment, physicists or scientists have tried all they can using the available knowledge of physics at the time to derive the distribution of blackbody radiation. In this case, Boltzmann tried to derive this using thermodynamics law, and finally it still end up with the Rayleigh-Jeans formula. What happened with Rayleigh-Jeans formula is that it cannot describe the blackbody radiation spectrum, and it fits only at low frequency. So come this guy Max Planck proposed his hypothesis. Basically, Max Planck found the correct formula and inadvertently developed the beginnings of quantum mechanics. So we can say that quantum mechanics started from Max Planck hypothesis. So Planck's idea was to modify the theory to make the mean energy of the particle as a function of frequency. Remember that in the previous slide, E is a function of temperature, but now Max Planck suggests that the mean energy of the particle as a function of frequency, not as a function of temperature. Planck assumed that E could no longer take on arbitrary values, but only discrete multiples of some fundamental energy. Remember that the Boltzmann in Boltzmann distribution, he used integration because the energy E is supposed to be continuous. That means the value changes continuously. But Max Planck suggested that E could no longer take any values, but only certain values. That means discrete multiple of some fundamental energy. Further, this fundamental energy should be proportional to frequency. Okay, that means now E can have only certain values. For example, E equal to 0, h nu plus 2h nu 3h nu, okay? So, and so on. That means it has discrete values, Stern values. It's not arbitrary, okay? Stern specific values. That's what Max Planck suggested or proposed. With this assumption, the mean energy equation can no longer be an integral, because integration is usually for continuously changing values. So it no longer be an integral over a continuous range of E, but should be a sum over the allowed discrete value. That's why Max Planck used the summation symbol here. That means basically it is sum of P, E, and so forth. Okay. Then the mean energy now is like this. Compared to the Boltzmann using classical physics, E mean energy E equal to kT. So you can see that now E, the mean energy E or the average energy E, is directly proportional to frequency, but also we have here frequency. And yeah, I mean completely different. That's why initially the scientists were not to say flattered, but were surprised that Max Planck proposed these new ideas. What are the new ideas? That E has discrete value. That means the energy E has discrete values, and E is directly proportional to frequency. Taking this expression for the mean energy and multiplying by the number density of waves, we obtain the Planck expression for the blackbody radiation spectrum. So now we have this energy density formula. Okay, it looks almost similar to the one using classical physics method, but you can see here that there is a -1 in the denominator. So if we plot this graph, energy density against frequency, then we can get that the Max Planck formula fit into the experimental data spectrum of blackbody radiation. So actually this is a, what you call it, a triumph, should I say, the success of Max Planck in describing blackbody radiation by putting forth hypotheses concerning the nature of the radiation itself, that the radiation should have discrete energies and the energy is directly proportional to the frequency. So there is some breakthrough, something very new at that time, and people initially was skeptic, but finally when later when Einstein, Compton used Max Planck's ideas in their works, then only then they found that what Max Planck proposed was correct, because it fits, or it is what you call it, coincide with experimental data. In conclusion, Planck managed to describe the spectrum of blackbody radiation by proposing that the radiation has discrete multiples of energy. The energy is a function of frequency and in the form of wave packets called photons. That's what finally in modern physics we sometimes we have to imagine that radiation is now in the form of photons. What do you mean by photon? Basically wave packet. Okay, like berkas-berkas gelombang lah. It is a form of wave, but it's not continuous. It is in packets and in parcels, which we call photons. So it looks more like a particle inside a packet. Okay. Thank you very much for your attention.